So I'm going to teach you how to do the equation E is equal to h nu. So it calculates the energy that a photon can have. E denotes energy and it is measured in joules. That's the unit. H stands for Planck's constant and it is a constant number. H equals 6.626 times 10 to the negative 34 joules second. Nu stands for frequency and it is measured in hertz or 1/2. They mean one and the same. So here is a problem that's asking us to use the equation E is equal to h nu. The frequency is given. We should make sure that we substitute it in hertz and not in megahertz. So substituting 6.626 times 10 to the negative 34 joules second times 9.47 times 10 to the 7 1/2. Second cancels, and if you know how to put numbers in scientific calculator, you get 6.626 second E negative 34 times 9.47 second E7. If you multiply, you get 6.27 times 10 to the negative 26 joules. So that is your answer to the first question. And the second question, the energy is given and you're asked to solve for the frequency. So your energy is 1.63 times 10 to the negative 15 joules equals your Planck's constant is 6.626 times 10 to the negative 34 joules second times your frequency. So in order to solve, you have to divide by your Planck's constant on both sides. 6.626 times 10 to the negative 34 joules second. So if I put it into my calculator, I have 1.63 second EE negative 15 divided by 6.626 second EE negative 34, and I get 2.46 times 10 to the 18 hertz. That's my answer to my second question. So if you look at the third problem, the frequency is given, the energy is asked again. So energy equals your Planck's constant, which is joules second times 3.0 times 10 to the 17 hertz. And my final answer for the energy is going to be 6.626 negative 34 times 3 second EE 17, and if I hit enter I get 1.99 times 1.99 times 10 to the negative 16 joules. But this is only 2 sig figs, so if I round I get 2.0 times 10 to the negative 16 joules. So an X-ray machine, this is the frequency of the rays that are coming out of the X-ray machine. So the energy is equal to my Planck's constant times the frequency that's coming out, which is 2.5 times 10 to the 12 hertz. And if I multiply these two, my energy will be 6.626 second EE negative 34 times 2.5 second EE 12. The energy that it'll give out in a second will be 1. This is just 2 sig figs, so 1.7 times 10 to the negative 21 joules this is per second that the energy is coming out. So if you want to multiply that by 0.1, you get 1.7 times 10 to the negative 22 joules of energy that's coming out from an extract. So we have gone over the Rydberg equation. We are now going to do problems with the Rydberg equation. We have done C is equal to lambda nu equations. We just did a few problems with E is equal to h nu. So we're going to use all this information that's on this page to do problems on the next page. Now, this very first problem is going from the ground state to the excited state, which means the electron is transitioning from n is equal to 1 to n is equal to 4. Therefore, it's going to absorb the energy, and the energy delta E is given by the equation negative 2.178 times 10 to the negative 18. It is, the final state is 4 squared minus the initial state squared. So substituting into the Rydberg equation, we have 2.178 times 10 to the negative 18 equals 1 over 16 minus 1. And so if I put this number in a calculator, I have negative 2.178 second EE negative 18 times, I can open up a bracket and say it's 1 divided by 16 minus 1. And I get my answer as 2.04 times 10 to the negative 18 joules. So since the energy is being absorbed, so it is positive. So this answer is, the energy is absorbed. As it goes to a higher energy level, it absorbs the energy. Now in this case, the energy is being released. So the value of delta E that we calculate will be negative 178 times 10 to the negative 18. My final is 2 squared and my initial is 4 squared. So now if I substitute an equation, I have 10 to the negative 18 divided by 1 by 4 minus 1 by 16. And now if I plug it into my calculator, negative 2.178 second EE negative 18 times, I'm going to open up my brackets, 1 divided by 4 minus 1 divided by 16, and I get my answer as negative 4.08 times, if you want, you can report to more than 466 times 10 to the negative 19 joules. That is the amount of energy released. Now, to release this energy, the electron needs to give off a photon of light. What energy does the photon have? Photon will have the same energy as the difference between the energy level, as the difference in energy between the levels. So the photon's energy will be equal to negative 4.084 times 10 to the negative 18 joules. So what is the wavelength that this photon has? Now in order to solve for wavelength, we need to look at the equation E is equal to h nu and C is equal to lambda nu. So substituting that nu is equal to C over lambda in the above equation, we get E is equal to hc by lambda, or lambda equals hc over E. since we are calculating the wavelength, we are going to ignore the negative side, and we're going to say that's the energy that's given off. That's 6.626 times 10 to the negative 34 joules second times 3.0 times 10 to the 8 meters per second divided by the energy is 4.08 times 10 to the negative 19 joules. So here the unit for my final answer will be meters. They want me to calculate the wavelength in meters and then in nanometers. So if I solve this equation, I'll first get the answer in meters, and then I will convert that into nanometers times 3.0 second E8 divided by 4.084 second E negative 19, and my final answer is 4.87 times 10 to the negative 7 meters. In order to convert that into nanometers, it's 4.87 times 10 to the negative 7 meters. 1 meter is equal to 10 to the 9 nanometers, and it works out to 487 nanometers. So that's my answer in nanometers. That's my answer in meters. So the sixth problem is asking us that there are various energy levels, but we don't know which energy level. From some energy level here, the electron is dropping down to the energy level n is equal to 2. It's dropping down to n is equal to 2. And when it's dropping, it's releasing a wavelength of 410.1 nanometers. They want to know what is this energy level from which it is dropping. So in order to calculate the energy, we use the equation delta E. We use the Rydberg equation minus 2.178 times 10 to the negative 18. We do the final, which is 2 squared minus, we don't know what the initial energy level is, and we're going to solve for that. Now, we know the wavelength. Since we know the wavelength, we can actually calculate the energy using the equation E equals hc over lambda. But we have to make sure our lambda is in meters and not in nanometers. So if I substitute in the equation 6.626 times 10 to the negative 34 times my speed of light, this is joules second, and divided by my wavelength 410.1 nanometers, I'm going to convert it into meters by multiplying by 10 to the negative 9. So now if I substitute this into my calculator, second EE negative 34 times 3 second EE8 divided by 410.1 second EE negative 9, I get my answer as 4.847 times 10 to the negative 19 joules. Now we have to remember that this energy is actually the energy that is given off, because it's coming in from a higher energy level to a lower energy level. So this should actually have a negative sign. Now if we take this energy and substitute it in the equation above, we get negative 4.847 times 10 to the negative 19 equals 1 times 10 to the negative 18, 1 over 4 minus 1 over ni squared is our equation. Now there is a negative sign on both sides, so we can get rid of the negative sign. And now solving, I'm going to get rid of this number before the equation, and I'm going to divide both sides by 178 times 10 to the negative 18. And so if I cancel I get 1 by 4 minus 1 by Ni squared equals, solving the left hand side of the equation, I get 4.847 to the power of negative 19 divided by 2.178 to the power of negative 18. I get 0.2225 and equals 1 by 4 minus 1 by n squared. Or in other words, if I bring 1 by n squared and I squared to this side, my equation becomes 1 by 4 minus 0.2225. And so if I do 1 divided by 4 minus 0.2225, I get 0.0275 is 1 by Ni squared, or in other words, Ni squared equals 1 divided by 0.0275, which is 36.36. Students are confused. Let me rewrite this step. Ni squared equals 1 divided by 0.0275, and it gives me this step. I have just switched the two variables, and so that I arrive at this. So if I now take the square root of this to solve for Ni, if I now take the square root of 36.36, I get 6.06 to the power of 5. I get 6.03 actually. 6.03. Now I'm actually solving for the initial energy level. The initial energy level cannot have decimal points with it. So they are fixed energy levels. So the initial energy level equals 6. So the electron drops from the energy level 6 to reach the ground state, and is equal to 2. We have one more problem that we need to finish on the other page, and this problem has the wavelength and of the light emitted by the transition n is equal to 2 to n is equal to 1 for a hydrogen electron. So we're first going to calculate the delta E, negative 2.178 times 10 to the negative 18 equals, the final is 1 squared minus the initial is 2 squared. So the energy equals minus 2.178 times 10 to the 18, 1 minus 1 by 4, which is nothing but 0.75, so negative 2.178 second E, negative 18 times 0.75 equals 1.63 times 10 to the negative 18 joules. Now we have to calculate the wavelength of the light emitted. So we know that delta E equals hc over lambda, or lambda equals hc by delta E, ignoring the negative sign because it is the energy released times 10 to the negative 34 joules second times 300 times 10 to the 8 liters per second divided by the energy is 1.63 times negative 18. If I substitute it into my equation, 6.6267 second EE negative 34 times 3 second EE, 8 divided by 1.63 second EE negative 18. I get my answer as 1.21 times 10 to the negative 7 meters, which is equal to 121 times 7 times 10 to the 9 nanometers, which is actually 129 nanometers. Now, if you look at the visible regions spectral lines, they vary from 400 to 700 nanometers, and this given light is less than 400 nanometers, so it's going to fall in the ultraviolet region of the electromagnetic spectrum. Because it doesn't exceed 10 to the 10, and it's in the range of the ultraviolet to the negative 7 to 10 to the negative, it's in the range of the ultraviolet rays. How much energy would it take to remove an electron completely from a hydrogen atom? So again, the equation is delta E equals negative 1.787 times 10 to the 18. Your final energy state is your infinity squared minus, let's assume the first energy level is where you're removing it from. So the maximum energy that you would require to remove the electron from the first energy level in hydrogen would be this, and 1 by infinity squared is nothing but 0 minus 1, and negative 1.178 times 10 to the negative 18. So if you end up subtracting 1 from your equation, it's 0 minus 1 is minus 1, so minus of minus will become plus, so you need to give this much energy to the electron to remove it from D, n is equal to 1, state completely out of the atom.